Okay, let's discuss basic exponential functions. And what I mean by basic here, it's not clear what I mean. What I literally mean is we're going to look at functions that look like this. F of x equals some number a to the x power. So notice I mentioned the variables in the exponent. This is what I mean. Um, that's what the definition of an exponential function is where the variable is in your exponent now. So some examples of exponential functions might be y equals 2 to the x, or y equals 5 to the x, or y equals 1/2 to the x. Okay? Specifically, we're only going to look at numbers here that are positive. All right? And that's for a good reason. If this number is 0, you get 0 to the x, and that's simply 0 in most cases. If this number here is negative, you get something really strange, and I'll sort of let you explore that. Maybe on your own, you could look at y equals -5 to the x and try to graph it and see what happens. For example, you should consider what happens in this case if x is a half or if x is a third. You know, you should get some interesting things going on there. So we're going to look at a values, numbers down here that are positive, numbers that are bigger than 0. And also, we don't want a to equal 1, because if we do, this becomes 1 to the x, which no matter what x is, you get this constant out, which is 1. So this function is not very interesting because the exponent has no impact on the function at all. All right, so we're going to look at these types of a values. So clearly what this does is we're going to look at bases here for this function. A is a base of this exponential function. The base is going to be a number bigger than 0. So here's 0, here's 1. Can't be 0 or 1. It's going to be a number between 0 and 1, or a number bigger than 1. So actually what we plan to do is only look at bases that are bigger than 1, and I'll show you why. Okay? So we are actually only interested in bases that are bigger than 1, not the numbers, not fractions basically, or decimals between 0 and 1. The reason for that is this. If you recall, take some number between 0 and 1 like 1/2. 1/2 is the reciprocal of the number 2. So 1/2 is the same thing as 2 to the -1 power. So what we've just done is taken this. If you want to, you could think about this as 1/2 to the +1. We've taken it and we've rewritten it as a base that's bigger than 1 instead of a base that's smaller than 1. So for example, if your function is f of x equals 1/2 to the x, you could rewrite that as 2 to the -1 to the x, and then -1 and x multiply in this case to give you 2 to the -x. So you've taken this function and you've rewritten it in terms of a base of a number bigger than 1. So you can do that when your base is a fraction, a number between 0 and 1. So let's analyze this base function. Let's take an example like f of x equals 2 to the x. Let's take this simple example. This is a basic exponential function. No transformations here. This is one of our base functions. In this case, if you plug in 0 for x, if x is 0, y is 2 to the 0 power, which is 1. So you get this ordered pair 0, 1. In fact, no matter what base you have here, no matter what a value you have, you're going to go through this ordered pair. Okay, so you should think about that. All these base functions go through 0, 1. All right. Now if x is 1, y is 2 to the first power, which is 2. So you're going to get a bigger value. If x is 2, you get 2 squared, which is 4. If x is 3, you get 2 cubed, which is 8. Right? So you can see as you go to the right, your numbers increase really quickly. And as you go to the left, if x is -1, you get 2 to the -first power, which is a half. So you're going to shrink by a half. If x is -2, you get 2 to the -2nd power, which is 1/4. So you shrink by a half again. And you keep shrinking by a half, but you're never going to reach the x-axis. So the x-axis is an asymptote in this case. Here's the graph of our base function.